All right, class. So we're going to look at chapter 6, and we're going to review for the exam. So you guys got passed out before, and we're going to go ahead and do the odds, and then you guys are responsible to do the evens for extra credit on top of the exam. So let's go ahead and get started. So these are the sections that are going to be included in the exam. So let's start with number 1. Determine whether the statement is true or false. If the statement is false, explain why. So for number 1, it's saying the total area under a normal distribution is infinite. So if you look at your notes, that's 6.1, then we talked about that stuff. So for a normal distribution, remember that your bell curve looks like that, and remember that it's continuous, it's smooth everywhere. The mean in the middle is 0 if it's standard, and the standard deviation is 1 if it's a standard normal distribution. And even though it goes forever in both directions, that doesn't mean that the area is infinite. The area is actually on contrary. The area, if you were to take the area under the entire curve, it would be 1. So the area under the curve is 1, even though the curve is infinite and never touches the x-axis. So an interesting property of the bell curve. So that was 6.1, one of the characteristics. So this is false. So number one is false because of this curve. It's actually, the area is equal to 1. So area under curve is equal to 1. All right, so number 3, all variables that are approximately normally distributed can be transformed to standard normal variables. So this is going from the x to the z, and this is true. You can do this because as long as they're approximately normally distributed, then you can convert an x value to a z-score using the z-score formula. All right, so that is a true statement. So for number 5, the area under the standard normal distribution to the left of 0 is negative. So it's saying that the area is negative. So remember, if you have the standard normal distribution, you have 0 in the middle, and you're going by 1 on each side, then it's saying that the area to the left of 0 is negative. But we know that's not the case. This is false. Because the area to the area can never be negative. The area in this case is 0.5 because you have half of the curve. It's not negative 0.5, it's 0.5. So area cannot be negative. So area under the curve cannot be negative. All right. So now let's look at number 7. The mean of the standard normal distribution is what? So 0, 100, 1, or its variable. So if it was the mean of the regular normal distribution, it would be variable. Depends on, what the mean of the original is. However, the mean of the standard distribution is always going to be 0, because remember, when you do it, just like we did here, just like we did up here, the mean is right there. It's going to be 0. So the mean is 0. So this answer is A. All right, let me go ahead and get rid of this. All right. All right, so now let's look at number 9. So which is not a property of the standard normal distribution? It's symmetric about the mean, it's uniform, it's bell-shaped, it's unimodal. So not a property of the standard normal distribution. So the standard normal distribution is, if we look at number 5 here, it's symmetric. You can tell that it's symmetric. It's not uniform. Remember, uniform means that it has the same, so this is how uniform will look like. Uniform means it has the same shape throughout. So the same numbers throughout, which that's not the shape. This is uniform, but it's not uniform, right? Because if you draw it out, it's like it's bell-shaped. So it's bell-shaped. So checks out for that. It's symmetric about the mean. So the mean is always in the middle. All right, so the mean is always in the middle, and it's symmetric about the mean. And it's so it says unimodal. So unimodal means you only have one mode. So here you only have one mode, which is at the very center. All right, so the one that is not a property would be B. It's not uniform. So the answer to number 9 is B. That's not a property. All right, so let's look at number 11. All right, so the standard deviation of all possible sample means equals what? So if you recall, the standard deviation of all possible means. So this is the standard deviation of the means. So remember the sigma x bar? That's a 6.4 concept, the central limit theorem. All right, so that is equal to the original population standard deviation divided by square root of the sample size. All right, so what does that match up with? Well, it's not A, because it says the population standard deviation. It's not that. The population standard deviation divided by the population mean, no, that's not true. That's according to this formula. The population standard deviation divided by the square root of the sample size, yes, that is what we are looking for. So therefore, the answer is C. All right, so let's look at number 13. So number 13 says the difference between a sample mean and a population mean is due to what? All right, so for this guy, remember that the difference between a mean and a population mean, so that's x bar minus the mean. So we know that from the central limit theorem that the mu of x bar is going to equal mu. All right, but that's the mean of the x bars. If you were to randomly take a set of data and do the x bar and subtract it from the mean, well, the x bar is not going to equal the mean. It's only when you do the average of the x bars. So like if you had 1, 2, 3, 4, 5, and you took a sample there, that's my sample of 2, well, the mean of that is 1.5. Right? And if you took a different sample, well, if I took that sample, well, the mean of that is 4.5. But the mean of the entire thing is 1 plus 2 plus 3 plus 4 plus 5, right? Which that would be 9, 12, 14, that would be 15. So the mean of this guy is 15 divided by 5, which is 3. So you see that when I take a sample and I average it, it's not going to exactly be 3. It's only when I take all the possible samples and I average those that it will give me the mu x bar. But if I take a random sample x bar and I subtract it, well, 1.5 minus 3 is negative 1.5. So what happened there? That's due to sampling error. Because when we take a random sample and we do the average, we're not going to get the mean exactly. So this is sampling error. So that's a vocab term from 6.4 when we did central limit theorem. So that's called the sampling error. All right, so Number 15. The standard deviation of all possible means is called the, so this is the sigma x bar. So the sigma x bar, the standard deviation of the means, we call that the standard error. So the standard deviation of all possible means is called the standard error. All right, number 17. The correction factor. Okay, skip number 17 because so cross that one out because there will not be a question on that on the exam. There will not be a question like that because we haven't talked about correction factor for central limit theorem. So you don't have to worry about that. Okay, we haven't talked about that at all. We skipped that. All right, so let's go ahead and do number 19. So number 18 is very similar to number 19, okay? So number 18, it says between 0 and 1.5. That's the same thing as this one, part A, where it's saying z is between 0 and 2.16. Okay, so just to keep, put that in perspective. I'm not going to do all of these. I'm going to do one of each type, okay? So I'm going to do, let's say, I'm going to do this one of each type of problem. And I'm going to do the greater than one, and then I'm going to do the less than one. Because this stuff was on the quiz. It's just a review. This was on the 6.1, 6.2 quiz. All right, so let's do those. So number 19. Let's do part C. So we want the probability that z is between negative 1.63 and 2.17. So in this case, we're going to, we got to show our work here, so we got to draw out the normal distribution, okay? So draw it out, draw out the standard normal distribution. So you got 0 in the middle, 1, 2, 3, negative 1, negative 2, negative 3. Label your negative 1.63. And your 2.17. And we want the z between those, so that means we need to find this area right here in between them. All right, so in order to find this area, okay, I need to find the probability that z is less than 2.17, so I need to find this probability, minus the probability that z is less than negative 1.63, okay? So that's the area to the left of that. All right, so and that'll give us in between. So we need to look this up on the z-score chart. All right, so we're going to do that now. All right, so we're going to go ahead and look it up. So if we go to the z-chart, we are looking up for 2.17. So let's do that one first. So 2.17, that's 0, 1, 2, 3, 4, 5, 6, 7. So this is 2.17, 0.985. 0.9850 minus, now let's do negative 1.63. I'll try to zoom in for you guys here. Negative 1.63, 0, 1, 2, and 3. 0.0516. I'll just round that. 0.0516. All right, so then now we are going to actually calculate that. 0.985 minus, and you should get 0.9334. All right, and that's your probability. All right, so now let's look at another one. Let's look at F. So we want the probability that z is greater than 1.77. So we're going to draw the curve. So 0, 1, 2, 3, negative 1, negative 2, negative 3. We want 1.77 here, and we want to the right, since we want greater than. So since we want greater than, you need to do 1 minus the probability of less than. Remember that the table gives you the less than automatically. All right, so we're going to do 1 minus the 1.77. So we're going to look that up on the table now. So 1.77. 1.77 is over here. 0.9616, we'll round that. 0.9616. All right, so we'll go ahead and calculate that. You get 0.0384. And that's your probability for F. All right, so let's look at G. So for G, you want the probability that Z is less than negative 2.37. So we're going to draw the bell curve. That wasn't too great, but it's okay. 0, 1, 2, 3. So negative 2.37 right there. We want to the left. So since the table automatically gives us to the left, we can just look up this number and call it a day for that. So negative 2.37. That's 0, 1, 2, 3, 4, 5, 6, 7. So there you go. 0.0089. We'll round that. 0.0089. All right, rounding to 4 decimals. All right, that's all there is to it, guys. So now let's look at number 21. All right. Let's zoom in a little bit on 21. All right, so the average height of a certain age group of people is 53 inches. So they give us the average height of a group of people, and this is assumed to be a population. So, all right, so let's go ahead and label that. That's our mu, which is 53. All right, so our mu is 53. The standard deviation is 4. If the variable is normally distributed, find the probability that a selected individual's height will be A greater than 59 inches. So we want the probability that X is greater than 59. All right, so that means my X is 59. My X is greater than 59. All right, so we're going to label the bell curve. So we know that the middle is 53. We are going by 4 on each side because the standard deviation is 4. Now we want greater than 59, so that's over here. 59 is there, and we want greater than. Okay, so we need to convert this to a z-score. So we're going to convert that now. So let's do that over here. So we got z is mu, let's write out the formula, x minus mu over sigma. All right, so we have 59 minus 53 over sigma is 4. So that gives us a z-score of 6 over 4, which is 1 2/4, so 1.50. All right. So now that we know our z-score, we can say this is we want the probability that z is greater than 1.50, which means that if we look up on the table, we need to do 1 minus the probability that it's less than 1.50, and then look that up on the table, because the table only gives us the less than. So let's go back to the table and look it up for 1.50. There you go, 0.9332. So 1 minus 0.9332, 0.0668. And there's the probability that an individual's height will be greater than 59 inches in this population. All right, let's look at part B. All right, so we want less than 45. So we want the probability that x is less than 45. So 45 is over here. We want less than, so shade there. Convert that to a z-score. So z is 45 minus 53 over sigma. And this is going to be negative 8 over 4, which is negative 2.00. And I do 2.00 because that's what the table wants. The table wants 2 decimals. So now we want the probability that z is less than negative 2.00. So since it's less than, we can look up the value on the table, and that is our answer. So let's look up negative 2.00. And that is 0.0228. 0.0228. And that is our answer for part B. All right, I'm going to do one of these parts. I'm not going to do both of those. All right, I'm going to do either C or D, so I'll just choose C because C and D are basically the same type of problem. So we want the probability that Z is between 50 and, or not Z, I'm sorry, the X, the height X is between 50 and 55. Okay. So again, I'm going to draw it out, show my work. We want it between 50 and 55. All right, so we're going to calculate that. So we have 2 z-scores to calculate for. So I'm going to call this x1, I'm going to call this x2, and I'm going to calculate those 2 z-scores. So z1 is 50 minus the mu over the sigma. So this is equal to negative 3 over 4, which is negative 0.75. And then z2 is 55 minus 53 over 4, which is 2 over 4, which is 0.50, positive. All right, so now, since we have 2 z-scores, we need to find the area for both of those z-scores and then subtract them from each other to get an area. So we want the probability that z is between negative 0.75 and positive 0.50. So that means we got to subtract the bigger area minus a smaller area. All right, then we look them both up on the table and to get the numbers. So we're going to look up 0.50 first. So 0.50 is 0.6915. 0.6915. Negative 0.75. 0, 1, 2, 3, 4, 5. This is negative 0.75. 0.2266. All right, so we're going to go ahead and subtract those real quick. 0.69. So you should get 0.4649. All right, so that's the probability of someone having a height between 50 and 55 inches. So it's still not likely according to the flip of a coin. It's less than 50% chance, but still bigger than the other ones. All right, so that's 21. I'm going to move on. All right, so we're going to go ahead and move on to 23. So the average number of years a person takes to complete a graduate degree program is 3. So that's 3 years. So mu is 3 years. Now it says the standard deviation is 4 months. So be careful with this one. This is in years, and standard deviation is in months. So we got to convert the months to years. So we got to do, there's 12 months in a year. So 4 divided by 12 is 1/3. So this is 0.33 years. Be careful with that, okay? Because I made that mistake before, and I want to make sure that you don't make that same mistake. All right. So now we want the probability that it'll take more than 4 years to complete the program. So probability that x is greater than 4. So I'm going to draw the bell curve real quick. So 4.33, 4.66, about 5. About 3.66. This is rounding, by the way, because this is 0.33 going on forever. And then 3.33, and then about 3. Oops, sorry, I'm sorry. The mu is 3. My bad. So this is going to be 3.33, 3.66, 3.4, 4 years here. And then this will be 2.66, 2.33, and about 2 years. Okay? All right. So now we got the graph. So we want x is greater than 4. So we want here, and that's my x equals 4. So we want greater than that. So that's to the right. All right, so we got to convert that to a z-score. So we got here z is 4 minus mu over sigma, which is 0.33, or 1/3. So this is 1 over 1/3. That's the same thing as 1/3, which is 3. So my z-score is 3, which we can tell because it's going 1, 2, 3. So that does make sense. So the z-score is 3. So we want the probability that z is bigger than 3, which means that we want to do the 1 minus the less than, because the table gives us the less than. We looked that up on the table for 3.0. So for 3.00, 0.9987. 0.9987. 1 minus that. So that means it's going to be 0.0013. So you got less than a 1% chance in order that it would take to complete the program in more than 4 years. All right, so I'm going to skip B and I'm going to do one of the other ones, okay? Because B is pretty similar. Let's do C, okay? And then we'll be done with this problem. So between 3.8 and 4.5 years to complete the program. So the probability that x is between 3.8 and 4.5. So again, draw it out. So x is, the mu is 3, yep, and it's going by 3.33s. All right, so we want between 3.8, around here, and 4.5. So 4.5 is, this is a weird looking tail. Let's continue this. 4.5 is around here. So it should be a very small probability because we only have that last portion of the tail. So this is going to be called x1, and then I'll call this x2, all right? So we're going to calculate z1, which is 3.8 minus the mu over the sigma, which is 0.33. So you get 0.8 over 0.33, going on forever. And you would get 2.40. Now let's do z2. So 4.5 minus 3 over 0.33, 1.5 over 1/3. You get 45. Or, wait a second, 4.5. Yeah, let me make sure. Yeah, 4.5. 4.50. All right. So now we can find the probability that z is between 2.40 and 4.50. So that means to do that, we need to subtract the probability that z is less than 4.50 from the table, minus the probability that z is less than 2.40, again, from the table. All right, so we go to the table, and notice that there is no 4.5. All right, so since there's no 4.5 here, we're going to estimate it to be 0.9999, okay? So this is going to be 0.9999. And then for 2.40, let's look that one up. 0.9918. Okay, so we'll subtract those, and you get approximately 0.0081. All right, and that takes care of number 23. So let's skip on, move forward to number 25. All right, so the average thickness of books on a library shelf is 8.3. So the average thickness is 8.3 centimeters. The standard deviation is 0.6 centimeters. So they're in the same units, so we're good. The standard, if 20% of books are oversized, find the minimum thickness of the oversized books on the library shelf. Assume the variable is normally distributed. So if 20% of the books are oversized, we want that minimum thickness. All right, so oversized means greater than, right? So we know that we're going to have some kind of distribution, and we know that 8.3 is going to be in the middle, right? And the standard deviation is going to be by 0.6s. So then this will be 9.5. That'll be 10.1, 7.7, 7.1, and 6.5. All right, so we know that we want 20% are oversized. So 20%, I don't know where that is on here, but that's what we're going to try to figure out, right? So we are trying to figure out what the x value is so that 20% of the books are oversized. And that is 20% or 0.200. Okay, so remember, 20% is a percentage, which means you're looking at area under the curve. So they're saying that the area to the right of the whatever x value is 20%. So we need to figure out what that x value is. So in order to find out what the x value is, we need to find the area to the left of it, because the table gives us the area to the left. So we need to do 1 minus 0.2000, and that'll give us this side. So this side of the curve is 80%. All right, so we're going to use that value and look that up in the table. Okay, that's an area. All right, so this is saying that the area is 0.800, not the z-score. We need to figure out what the z-score is that corresponds to this. All right, so we need to convert this to a z-score. So let's go to the table. Table is we want to look up for the area of 0.8000, as close to that as possible. So if you look here, we have 0.802, 0.7995. That's the closest one to 0.800, so we're going to use that. So that means that the z-score that corresponds to that is 0.8, so 0.8 0.84. So 0.84 is going to be my z-score. All right, don't never matter the fact that these are similar. They're not always going to be similar numbers. All right, sometimes they'll be way different. All right, but the z happens to be 0.84. So now we know what the z-score is. So now we can go ahead and find the x. So in order to find the x, we're going to use this formula. So it's mu plus z sigma. Okay. And then we know what the mu is. The mu is 8.3. So we're going to do 8.3 plus, we found the z-score is 0.84. And the sigma is 0.6. And that'll give us our x. So this gives us 8.804. So about 8.8. So that means that the books are about 8.8 centimeters thick. All right. So this is about 8.8. All right. And notice I was off here, right? So I guessed that it would be between 8.9 and 9.5, but it's not true. It's actually between 8.3 and 8.9. So I'm going to just draw that out and correct that. Okay, is that the same numbers that I had before? Yeah. And then 7.7, 7.1, and 6.6. Okay, so it's actually 8.8, and then that is worth 20%. Okay, so that's the graph for the scenario, but the answer is 8.8 centimeters. All right, so that takes care of 25. Let's go to 27. So the average repair cost of a microwave oven is $55. So mu is $55 with a standard deviation of $8. The costs are normally distributed. If 12 ovens are repaired, find the probability that the mean of the repair bills is greater than $60. So they're saying the mean of the repair bills. So they're saying the probability that the mean of the repair bills is greater than 60. So this is not a x problem. This is not an x. This is an x bar. Since it is an x bar, that means we're using central limit theorem. All right. Since we're using central limit theorem, we need to know the sample size. So the sample size is 12 ovens. And because we're using the central limit theorem, we need to know what the sigma x bar is. All right. So the sigma x bar, the standard error, is sigma over square root of n. So we need to calculate that. So it's 8 over square root of 12. So we'll get what that number is. Um, 2.3. So we'll round it to 2.3. So $2.30, just about. All right, so I'll do 2.30. Okay, so now in this case, now since we are doing the central limit theorem, when we draw the curve, I'm going to draw a skinny curve, right? So the central limit theorem, the bell curve is a skinnier version of the original. The mu is still going to be 55 because by the central limit theorem, mu x bar equals mu. So mu is 55, so that's also mu x bar. And we are graphing x bar here instead of x. So 55, 57.3, 59.6, 61.9. Subtract, so you get 50, 52.7, 50.4, and 48.1. All right, so hopefully I did that right. Did that mental math. So that's the bell curve. Now we're going to do the probability that x bar is greater than 60. So 60 is right around here. And we want greater than, so we want to the right. So shade to the right. All right, now that we got this, we're going to convert that to a z-score. So you remember, since this is an x bar, you're going to use the x bar formula, which is that. Okay, this is the x bar formula for z. So we have 60 minus the mu. Mu is 55. We already calculated this. That was 2.30, just about. So we'll get that number. So I get about 2.17 for my z. So now we want the probability that z is greater than 2.17, which means we got to do 1 minus the less than, because the table gives us the less than. Then we can look it up. So 1 minus, look at the value on the table, 2.17, 987, this is 2.17, so 0.985, yeah, 0.9850. So 1.9850, which is 0.0150. All right, so that's the probability that the mean of the repairables will be greater than 60. That takes care of 27. Now we're looking at 29. Sleep survey. According to a recent survey, 38% of Americans get 6 hours or less of sleep each night. If 25 people are selected, find the probability that 14 or more people will get 6 hours of sleep, 6 hours or less of sleep each night. Does this number seem likely? So this is an average, okay? So according to a recent survey, 38% get 6 hours or less. All right. All right, so let's finish this up. So we got 25 people are selected. So this, okay, so looking at this, 38% get, 38% get 6 hours or less sleep a night. Okay, so that's telling me, since we're looking at percentage and all that stuff, this is a binomial. So do you either get 6 hours or less sleep a night, or do you not get 6 hours or less of sleep at night? So this is a binomial scenario. Just kind of looking at the percentage kind of gives it away. So it gives you like a probability of success. All right, so it looks like we got a probability of success here, 0.38, which means that the probability of failure is 1 minus 0.38, which is 0.62. So that's our probability of failure. In this case, if 25 people are selected, so n is 25, we want the probability that 14 or more will get 6 hours of sleep. All right. So in this case, we need to remember that oh wait, well, am I missing anything else? Okay, no, that's it. So remember that one of the first things that we do. All right, so one of the first things that we do is we determine if we can use the normal approximation. So we're going to see if we can do the normal approximation here. So this is like a normal approximation problem. So we're going to do NP greater than or equal to, that has to be greater than or equal to 5, and Q has to be greater than or equal to 5. So we know that NP, so 25 times 0.38, so if you do that, you get 9.5, which is certainly greater than 5. And then this one, you got to do 25 times 0.62. If you were to do that, you would get 15.5. I want to double check that. Yeah, 15.5, which is greater than or equal to 5. So it checks out. So we can do the normal approximation. So step 2, we want to determine the mu and the sigma. So the mu, we calculated that was 9.5. And then we need to determine the sigma, which is square root of NPQ. So NP is 9.5 and Q is 0.62. So we'll be able to get that number. So you get 2.43. So that's our sigma. All right, so it takes care of step 2. So step 3, if you recall, is to write out what they're looking for. So they want the probability that, look it up here. They want the probability that 14 or more people will get 6 hours of sleep. So they want 14 or more. So greater than or equal to 14. All right, so that's it for that. Now for step 4, you need to do the correction factor. So you can use a table or you can look at, do some logic with the table. So we want to include 14, right? 14 or more. And they want or more, so that's greater than. So we want on the right side. So in order to ensure that we include 14, we're going to go a little bit backwards and then do greater than. Okay, so go a little bit backwards and then do the greater than. And that'll ensure that we include 14 in our results. So that means we need to go 13.5. All right, so that's our correction factor. So if we were to go x is greater than or equal to 13.5, that'll ensure that we include 14. All right. All right, so now let's go ahead and do step 5. I'll do it over here. So step 5, we're going to calculate the z-score and all that stuff. So z is equal to x minus mu over sigma. So 13.5 minus the mu. The mu we calculated was 9.5. The sigma we calculated 2.43. Okay, so we'll calculate that, see what that is. So I get about 1.65 for my z. All right, so if I were to draw the scenario out, 0, 1, 2, 3, negative 1, negative 2, negative 3. So 1.65 is here, and we want greater than. So we want the probability. So step 6, we got to find the area. So we want the probability that z is greater than 1.65, which means we got to do 1 minus the probability that it's less than, because remember the table gives us the less than. So we're going to go to 1.65, 0.9505. So 0.9505. Then you subtract this, you get 0.0495. All right, so that's your probability of being greater than having that 14 or more people will have 6 hours or less sleep each night. It's not very likely because that's a very small percentage. So this is about 4.95%, which is not likely. All right.